Come on. There we go. Oh, burr. Crickets, crickets. Nobody's here today. Sound check, check, check. All right, we're working. Oh, hey, Guts. How are you, buddy? I'm not showing any viewers on my stream here. That's okay. Must be something on my end. So, that's okay. So what do you need help with, man? Let me know. Yeah, it seems to be working. So, yeah. Let me check something here real quick. Yeah, everything says okay. All right. Whatevs. Yeah, we'll work on whatever you want today, man. But I got a couple things to cover here. And we'll see if anybody else hops in there. Otherwise, today will be a really easy trivia day. So, but yeah, let me know if there's anything that you want me to cover here in the video today. Otherwise, we'll be back on Wednesday, like usual, down in the office there. And we only got 2 more weeks of that, this week and next week. And then just keep that in mind. After that, we'll go back completely to the live stream. Although last week we may have like a Zoom call or something that's like, what do you need me to cover? I will cover it again. Because here we are on the 5th. So yet this week here, next week, and then this week here, the 19th. I don't know if you can see that. My mug might be in the way. That's our spring break. Hey, Morgan, how are you? All right, we got a few people popping in there. So we are getting close to the end, though. And so I've been looking at Alex's progress for most of the folks out there. And some of you are doing really well. Some of you, I'm starting to get a little bit nervous with the fact that you're getting a little bit behind. And so make sure that you're pushing past the purples this week and into the blues, because the blues, and particularly the dark blues, they should take you a couple weeks to do. Just so you know, I do have videos up on every topic in there. All right, so I know on my YouTube channel they're not organized particularly well. I can't really reorder them very easily. But they are in the playlist there, and so if there's anything in these chapters that you're dealing with confidence intervals or hypothesis testing, definitely go definitely go check those videos out so you can get a little bit of a leg up on the last little bit. And so I was looking at mine here, and so I'm almost done with my purples. We're going to move into the blues here today. I can't remember how many of these I have left. Let's just see. 14, I have 4 remaining. Let's go ahead and murder those off here real quick. And let's see which ones they are, because they should all be ones that you can actually skip. So, yeah. All right, so there's just 3 of these. T distribution, F distribution. Oops. Chi-square distribution, central limit theorem, sample mean. So, yeah, let's just go ahead and do these. So T distribution here, these are exactly like the Z distribution problems, except for the T distribution, or the student's T distribution, is a slightly different one. It's shaped the same way. The only difference about it is that when we use the T distribution, we will always be dealing with sample mean and sample standard deviation rather than population mean. and population standard deviation. So Z is for population, T is for sample. And that means that we have to introduce a slightly new concept called degrees of freedom. All right. And so degrees of freedom is very straightforward. It basically, I mean, all right. So we could go into a long mathematical complicated discussion of why you need to use degrees of freedom. All right. But really, the only thing that you need to know about degrees of freedom is that it just gives you a little bit of wiggle room in terms of your calculations. And it requires a different table lookup. All right. And that's it. All right. So that's, I mean, you don't really need to think about it much beyond that, because really what it does is it just introduces a slight amount of uncertainty into our calculations. And so, and degrees of freedom is really easy. It's whatever your sample size is. So like N, so your sample size, say it's 30. Your degrees of freedom would be 29. All right, it's always n minus 1. That's your degrees of freedom. Okay, and if we go through the calculations, you can see why that is. All right, so of course we have to use our sample size when we're calculating any of our z statistics, but with the students or the t distribution, we just have to use a slightly smaller sample size. That's all. That's all there is to it. All right, and so these ones, just like the ones before, where it's going to ask you to consider a t-distribution with the 30 degrees of freedom, compute p, probability of finding a t-score. It's not actually called t-score. Value of t less than, that's between negative 2.0 and positive 2.0. And so these ones are pretty straightforward. So like this one here, all we do is take one, subtract the other, and then punch that in to the calculator, and then it's going to ask us for consider that, and then so we would find out the probability with that one right there. And then so this one, consider a t-distribution 25 degrees of freedom, find the value of c. C of course is your cutoff value, where p is the probability of finding t that is less than or equal to c would be 0.10. That one, this is the one that people get a little bit screwed up on, but it's really straightforward. You're just going to use this button here, all right? And so just like the Z's, you're using the T's, so just like these over here. But this one is your T table lookup, and this is your probability one right here. And so just to illustrate how this would work, so notice that this one is the opposite of this one. Okay, so alligator eats the T on this one. So it's a left-hand lookup, not a right-hand lookup, and that does screw people up. So in this one, you're going to take your greater, subtract your smaller value. But you always have to do this DF, degrees of freedom. And so it's going to give us our degrees of freedom right there, 30. And then we're going to do another one in here, minus negative 2.00 with 30 degrees of freedom. And see, we got the opposite. That's because I did it backwards. All right, so yeah, sometimes when you do it like that, you get it backwards. Let me just see. Oh yeah, it took the smaller one and then subtract the larger one. So my bad. So, and then of course that's your answer there. So in this one, we just flip it around. Sometimes when you jack it up, just flip the sign on it. You probably did it. And if you do, actually, if you do this one where it's this probability one here and you get a negative answer, it's the positive one. You can't get a negative probability. All right, and then this one right here is really straightforward. 25 degrees freedom. So the probability would be 10%, okay? And so this is a right-hand lookup on this one, and so we're just going to take 1 minus this, all right? So 1 minus 0.10, so you give us 0.90, and then punch in your degrees of freedom, 25, bam, there you go, right like that. Easy breezy, and so that gives us our cutoff value right there, okay? Let's go ahead and kill two of these off. I'll probably jack one or two of them up, so... but this is the important one to do. You don't need to do the F distribution or the chi-square one just quite yet. All right. I mean, if you want to kill them off, that's fine too. But we don't use those until you get to the dark blues. And so don't worry about them too much. Okay, so probability of t, 1.1. See how this one lines up exactly like this, So we can just punch this one in directly, 9.1 with 25 degrees of freedom. Bam, bam. There we go. 0.33. Oh, actually, no, that's not right. Okay, so that's right. So since this is a left-hand lookup, we actually, when it's this way, right, like this, unlike the Z one, when it's like this one, you have to subtract from 1. So this one's P minus T, 1.91 with, oh no, actually that was right. My bad. So yeah, the probability of getting a t-value that's greater than 1.91 would be very small, okay? And so, sorry, ignore what I just said. If it looks like this, just punch it in directly. There we go. With 25 degrees of freedom. There we go. Did I do that wrong? 1.19, 1.91. There we go. See, and if you understand normal distribution, after a little while, you can kind of look at these things and say, like, oh, that can't be right. I totally jacked that up. How many? 3 decimal places. 0, 3, 3, 4. There we go. You do have to do them eventually, but I mean, if you're stuck on them, you move on to the blues, okay? Because the chi-square and the F distribution, you won't see them again until we get to the dark blues, all right? So, you know, make sure you do T and Z, all right? Because you need those in order to do the any of the hypothesis testing, okay? Later on in the dark blues, yes, you will have to do chi-square and the F distribution to unlock some of those more difficult problems way there at the end. All right. So no, I'm not letting you off the hook on them. I'm just saying if you don't feel like doing those right now, those are things that will unlock dark blues. So if you're not there yet, it's okay. Just make sure you're doing these. All right. T distribution is 16 degrees freedom. Oh, this one works just the same. So what you do with this one when it's split like this, so you 1 minus 0.95. Oops. 1 minus 0.95, okay? So you take this, subtract it from 1, chop it in half, odd 0.025, punch that into this T box right here, and then enter your degrees of freedom. So there you go. So that'd be 2.11, 120, right? Check. There we go. Easy breezy. All right, so here's one. And so remember, because I jacked this one up before, take your smaller value when you're talking about T and subtract your larger value from it. So there you go. They're already up there. I've already got them up there. Yes, I can make another one if you so choose, but they are, well, this is T right now. So, but I do have videos up on all of these, if I'm not mistaken. I know there's like 40 some videos in there, so just keep scrolling through until you find the one that has the exact title, just like this one. Sorry, I don't know how to sort those in a way where it makes a little bit more sense. F distribution, I definitely have one on F distribution. So there's definitely one. And F distribution isn't that hard. We can do it here today real quick if you want. But both of those are a little bit different. Oops. God dang it. So I'm not paying attention to what I'm doing here. So 1.04. So it is the smaller minus the greater. Yes. With 21 degrees of freedom. There we go. That looks about right. 0.68690, and then this one P to T .01, so this can be .99 with 16 degrees of freedom. Is that right? Probability that you'd have a T value with a cutoff less than 1%. Yeah, that's gonna be really small. So -0.25. Well, really far to the left. Let me put it that way. 8.3. There we go. Check. Cool. Let's do one more. So I think I've seen all 3 types in here. So this one looks exactly like that. So let's just punch it in. -1.9 with 20 degrees of freedom. Bam. And yep, that looks right. 0.964. So that's, remember, probability is always out of 1. And so, you know, -1.9 is way down here on this end. So most of it's going to be to the right of that. And so once you kind of learn that, you know, you can look at these and, I screwed that one up. Or you'd be like, nah, that one looks good. And so you get this one with the C's on either side, really easy. Just take 1, subtract the probability, .99 right there, chop it in half, and then punch that in here. And with 24 degrees of freedom. Dunzo. 796.7. Man, I'm getting weird rounding ones today. 7. So that would be 797, right? Yeah. There we go. Done. All right, next. Yeah, let's go ahead and we'll just go kill those other two off. I don't remember. I think F distribution is pretty straightforward. Just to understand, the F distribution looks a little bit different. It's got a big hump, and then it's got a little skinny tail way out there. So it's very similar to the exponential distribution, which we don't really cover in this class. It's very commonly used in things like manufacturing, production schedules, things like that. All right. And chi-square looks almost exactly the same. All right, so they're not normally distributed, so you can't quite use the same level of judgment with these, but they're also a little bit more simple to do. And when you get to ANOVA tables, which is in the dark blues, or the light blues, sorry, my bad. Yeah, the light blues are harder than the dark blues. It's very, very important. It's very easy to calculate too, though. All right. So, but just like the T distribution, notice that it faces the different way. The Z is the only one that faces to the right. These all face to the left, so they're left-hand lookups. And that's because the F distribution, it always starts at 0. So 0 is always your anchor point. All right, it's your minimum value. And so 0 is down here, and then the F distribution, it just goes up and up and up and up the further right that you go. All right, so there's no negative values in it. All right. Which makes it a little bit more simple. But let's see. So they're going to give us this problem here like this, and so we're going to subtract the lesser or the greater from the lesser, and then with the lookup, it's always, you just punch it in directly if I'm not mistaken. All right. Yeah. Now, the one thing that F distribution does have is it has what's known as numerator degrees of freedom and denominator degrees of freedom. That probably won't make any sense until we get to ANOVA. Okay, so I'm not going to sit there and try and explain it right? Without making you do ANOVAs. All right, once you do it at ANOVA down the road, it'll be like, oh, that's what that is. Okay, so don't worry about that right now. Just understand that it has 2 degrees of freedom with each one, and that's. No, I'm not going to explain it. Don't worry about it. So, just do the thing that it says. All right, so here we go. Let's give it a shot. All right. So so this one is backwards. All right, so notice the sign. And so this one we're going to have to do a 1 minus P of F. And then notice it has this F value right here. And so that one we're going to punch in this 0.65. And then DFN and DFD, so this is numerator degrees of freedom, and this is denominator degrees of freedom. And so that is given to you in the problem. 22 and 8. Bam, there we go. So, and don't try and interpret these just quite yet. They are a little bit, 201, 3 decimal places? Yeah, 201. So, they're a little bit difficult to understand, but if you get an F value that's like 37 dot something something something, it's probably wrong. Okay, not necessarily, but probably. All right, and again, when we do ANOVAs, that'll make a little bit more sense. All right, and so here we go. So F distribution 42 numerator degrees freedom and 43. Find C that's blah blah blah. And so this one we just punch this one in directly, I think. So this is going to be 0.95 greater than 0.05. No, I think that's the other way around. So it's going to be 0.05. We'll check our answer here real quick with 42 and 43. Be careful. Notice that these numerator and denominator degrees of freedom change from this problem, part A, to part B. Now, let's check that out. 1.66. Yeah, that's right. 1.664. Check. There we go. All right, so if this is facing this way on this problem, so if the alligator's eating the F, all right, subtract from 1 when you're doing this. If alligator's eating the C, then just punch it in directly. All right, there's your rule for this one. Here we go. Let's do this one. So with this, remember probability of F, and so we subtract the greater from the lesser, 0.85, with 19 and 35, 19 and 35 degrees of freedom minus, again, oops, what the heck? PF minus PF, there we go, I hit the wrong one. PF of 1.05 with 19 and 35. Yeah, man, that's kind of a pain. That's a lot to type in, but that's okay. 0.202. 203. There we go. Yep, looks about right. And then this one right here, find C. And so in this one, .05. What did I just say? Alligator eats the F. We just punch it in directly, right? Yeah. So with 40 and 33. 1.75. Yep, that looks right. 5, 6. There we go. Check. Ta-da! So F distribution. Oh, we're going to make us do one more here. Let's do it. All right, so this one here, again, notice it's backwards. So this one is greater than. This one here is F is greater than. This one is F is less than. And so we got to do a 1 minus. Oh, no, wrong one. This one right here, 0.65 with 25 and 21. And remember, these are just table lookups, all right? So this is just a step that you're going to have to do to help you down the road when we do a little bit more complicated analysis on this, so that you understand how the probability function in the calculator works, because that's how you'll make conclusions in the future. That'll make sense when we get to hypothesis testing real soon. And so here we go. This one is alligator eats the F, and so this one is the one that we punch in directly, if I'm not mistaken. So .1. DFN 48, DFD 25, bam, there we go. Yep, that looks right. 1.611, check. Cool beans, there we go. All right, so if you do that one with the F distribution, then just go kill off the chi-square one, because it's almost exactly the same. Notice that the symbols are just changing a little bit, and the symbol just denotes which actual statistic or which distribution we're working off of. Okay, and chi-square and the F distribution are very similar. They got a big hump on one side and a long skinny tail on the right-hand side. And the reason for that, again, well, it's for reasons. So, long story short, is that we use these when we're actually comparing categorical data, so categories against each other. And so, of course, the more categories you add, the more rare something would become. That's kind of the idea behind it, in a very simple sense. And so, like I said, we use these in production. Chi-square in particular, we use in nominal data analysis. So anyway, that's okay. Don't worry about that. All right, let me just show you how to do them. All right, so it's going to ask us two things. So this one's got 3 of them in here. And so this first one, suppose chi-square follows a chi-square distribution with 14 degrees of freedom. So you just have 1 degree of freedom with chi-square. Compute the probability that chi-square would be less than or equal to 9. Round your answers. And so in that one, we're going to use the Alex calculator, but instead of using this button or this one, we're going to use this one right here. All right, and notice that this one is in there directly like that. Okay. And so this one here is not. All right. So see how this one faces the other way? And so for this problem here, we're going to have to actually do a 1 minus chi-square probability table lookup of 9 with 14 degrees of freedom. Bam, bam, like that. There you go. All right. And so there's our answer right there. And so this next one here, you would punch this one in directly, because this one works. See how this lines up? Lines up like that. So .1 with 14 degrees of freedom. Punch it in the calculator like that. 1. So wait a minute. Did I screw something up there? Oh, this one you're looking for K. So K is your cutoff value. My bad. All right, so rather than a C, we're using a K. And so this one, you're going to use this button here. Okay, .01 or .1 with 14 degrees of freedom. This will actually give you your cutoff value, K, or that's what we use when we're talking about chi-square. So 21.06. And then find the median of the chi-square distribution with 14 degrees of freedom. This is the one that usually screws people up, but it's actually really easy to do because you're going to be doing the exact same thing on every single one. The median value in chi-square is whatever this value is, halved, all right, the half .5, okay? So, and it's always going to be the same. It's always going to be .5, and the only thing you actually have to do is put in your degrees of freedom. And it'll give you basically your median value with that degrees of freedom. So 13.3 0.33, whatever that means. That would be our median value, which would be the middle one right here in the chi-square distribution. Okay, and so this one, yeah, it jacks people up, but it's actually the easiest of the three to do. And so just do chi-square. Here, let's just do some. I'll show you real quick, and then we'll play some trivia. What's our topic for the day? So we just did Stranger Things in the previous class. Anybody else got a TV show they love? So I'd be happy to do it today. So here we go. So it is the lesser minus the greater. And so 4 with how many degrees of freedom? 7. 7 minus probability chi-square of 12 with 7 degrees of freedom. There we go. 0.679. Okay. K on this one. So that's where we use this button right here. And K dot 0.05 with 7 degrees of freedom. Bam. There we go. 14.067. Oh, actually, it only wants 2 decimal places. Sweet. Sabrina the Teenage Witch. Oh my God. You're talking about... Oh, jeez. You're dating yourself there, buddy. Oh, actually, no. I'm thinking of... oh, no. I am thinking of Sabrina. Yes. So, I am thinking of Sabrina. So, all right, man. We'll do it. I'll see if I can find a site. Good luck. So, let's see. I mean, unless you got something else in mind. Anyway, median value, 0.5. Always 0.5 on these. And then 7 degrees of freedom. There we go. 6.345. 2 decimal places. 6.35. Yeah, I want to feel young again. All right, you got it, dude. So, there we go. You got it, buddy. We'll see what we can find. All right. So this one here, notice that it faces the different directions. So you got to do our 1 minus 6 with 6 degrees of freedom. There we go. 0.576 or 3 decimal places. 3.77. There we go. Next one here, we're going to use this guy. 6 degrees of freedom, K greater than 0.05. 0.05. Oops. 0.05 with 6 degrees of freedom. Bam, there we go. K on this one is 12.59. 2 decimal places. Yep. And then this last one, the median value, we're going to do the exact same thing, except for median value is always 0.5 and 6 degrees of freedom. So there we go. 5.34. 2 decimal places. 3.5. There we go. Check. Dunzo. Oh, wait. We got to do one more. Sorry. Getting a little excited there. All right. So this one, always subtract the greater from the minor, from the lesser. And so here we go. Greater 5 with 8 degrees of freedom minus 11 with 8 degrees of freedom. Oops. There we go. 0.556. K on this one. Just have to do the table lookup here. 0.025 with 8 degrees of freedom. There we go. K value 534 or 53. There we go. And the median value, really easy, 0.5 with 8 degrees of freedom. 0.34. There we go. Check. All right, so those are pretty easy. All right, you know, once you get in the mood for them, just knock them all out. Just crush them all out. Just realize that you're basically gonna be doing the same thing on each one. Just pay attention to whichever way the sign is going, because remember, it's a little different on the Z calculator for reasons. And then you know, it's the same on all the other things. All right, so here we go. Teenage Witch. I don't think I've never had this category requested before, so I am excited to see what's out there. Let's see. Oh, I remember this. What food is Sabrina so addicted to she's not even allowed to have a single bite of it? I remember this. What food is Sabrina so addicted to she's not ever allowed to have a single bite of it? What is it? I remember that. Congratulations, Guts. You made me feel young. So, yeah. That's correct. Good job, Squidson. You got it. It's pancakes, so it's called Pancake Madness. So, which was a running theme for a while. Yeah, let's see. Uh, yeah, there's some good ones on here. Oh my goodness, there's like 30 pages of these. Holy crap. All right, there you go. Well, now, good job, Harley, but Squidson beat you to it. Did you know that, or did you have to Google that? So either way, that's okay. All right, last of our ERPLs here is central limit theorem, sample mean. This problem is way easy. Let's dive into it. So central limit theorem is a really important concept in statistics, but it's pretty basic. All right, you got a little example of it right here. But the way that I want you to think about it is basically the larger your sample size gets, the more accurate the more accurately it reflects your population. All right, and so and the thing about central limit theorem, and in particular, what makes it so important is that it allows us to make inferences about very large populations using very small samples. Okay, as long as that sample is randomly selected in one way or another, you can actually make really, really good inferences about a population as long as you get your sample size up. All right. And so there's different cutoff values for this. All right. So the kind of the rule of thumb one is if your sample size is randomly selected from a larger population, and if it's somewhere over 30, all right, you're usually pretty good. Okay, so you can make inferences about your population and its distribution just using sample mean and sample standard deviation, because rarely in the real world do we get our hands on population standard deviation. It's very, very rare. And so that is the central limit theorem in a nutshell. Okay, we could get into the law of large numbers, things like that, but quite honestly, this is just how survey research works. Okay, so and because it's a theorem, it's basically a law. All right, like the law of gravity, or things like that, or the Pythagorean theorem is the same thing. All right, so we can use it to do a lot of really cool things in statistics, which I'm sure Dr. Holman will put you through in 360. Right? So, but at the same point in time, actually doing these problems is a little intimidating. Okay, because you're going to use the Z formula right here. All right. And then actually comparing that to the data set that it actually gives you. Okay. Because really what it's asking you for here is, let's see, which one? Find the probability of observing a sample mean of 31.8 grams of fat per pound or less in a random sample of 35 farm-raised trout. And so the way that you have to do this one is that you'll have to use this probability key here in the calculator, this guy, because we're dealing with Z distributions here. And then you have to fill out the entire formula. Now, you can do this in the calculator. It's actually not terrible. Okay, so what I would do is I would do this part first. And so this is just your simple Z formula here, okay, to figure out the Z value, okay, which is the Z score, which is this guy right here. And so this is going to be sample mean minus... no, this is going to be X bar, which is your sample mean minus the population mean, all right, which gives to you right there, 32 grams. Okay, all over 7, which is our standard deviation, over the square root of our sample size, which is 35, all right? And so here, let me just kind of walk you through that one. The way that you want to punch this one in the calculator is you want to take whatever your value, your X bar, which is your sample mean, subtract your population mean first, all right, put that in there, and then divide that by your sample standard deviation, and then hit your divide key again immediately, and then hit the square root by your sample size, and boom, there you go. See, that's how I got that guy, right, like that, and then you just hit this button here, because it's facing the right way, and then hit enter, and ta-da, you get your answer. Okay? So now the reason why you're doing this in some respects is just so that you can actually see, like, okay, what's the probability that this sample that I specifically have here with that has 35 trout in it, all right, what's the probability that it's going to be less than, okay, the population mean, which is this guy right here, the probability. And so figuring out the probability requires all of those steps. Now, you can do it that way, okay? It's pretty straightforward. Or you can head on over here to the course modules. And, ta-da! There's a new Sabrina now? Nuh-uh. No way. So, actually, I think I heard that. But anyway, go over here to Module 3, Distributions, Confidence Intervals. And then here's a calculator that I built for you. You can use this. Okay, that's absolutely fine. Central Limit Theorem for Sample Means Calculator, XLS. Download. Take a little peek-see at it right here. And all you have to do is enter the information into the yellow boxes, and it'll spit out what you're looking for in the gray boxes. So let me show you how this one works. Okay? And again, this is just because, you know, I don't want you, Jack, you're getting too frustrated with the math. The math isn't that big. Where's my Alex? Did I murder Alex off here? No, there it is. So, here we go. Uh-oh. What's going on with my stream here, man? What is up with this? This seems to happen during this class. Well, let me know if we're getting jacked up here, so sorry about that. Stream health is extremely poor at the moment. Lame. Man, it only happens during this class. It's suck. Hmm. What do you mean not receiving enough video? I don't get this. Huh. Okay, if I'm fine for you, then we're just going to keep going. I don't know. YouTube's just messing with me. It's been doing that lately. I need to get the Comcast, although I don't want to. So, but anyway, here we go. Using my calculator, all you have to do is pick out the information from the problem that you need in order to complete it. All right, I need my mean, my standard deviation, my sample size, and my hypothesized mean, which is also my X bar. Okay, and so we'll go back to that. And so, a soft drink company has recently received customer complaints about its 1 liter size soft drink products. Customers have been claiming that the 1 liter size products contain less than 1 liter of soft drink. 1 liter of soft drink. The company has decided to investigate the problem according to company records when there is no malfunctioning in the blah blah blah. The bottle contains 1.02 beverage on average, with a standard deviation of 0.15. So always look for this. This is going to be like your mean, okay, and your standard deviation. So 1.02 and 0.15. We're going to go and we're going to punch those in the calculator. 1.02. And what was the sample size? Gosh dang it. Standard deviation was 0.15. 0.15. There we go. Sample size, go back to your problem. Take a look. We're going to pull 70 bottles. So 70 bottles. And find the probability of observing a sample mean of 0.993. Okay, and so the mean amount of that is 70 was 0.993, and so that's my X bar right there. So 0.993. Yep. Okay. You might have to do these the other way around, but that's okay. So anyway, so this thing right here, using the exact same formula I just showed you in the Alex calculator, does all the math for you. All right, so B6 minus B1. So these are backwards here because we got to do, yes. So this one's going to be 0.993. And this one's going to be 1.02, right? Bottles contain 1.02 on average. Sample 70 bottles, mean amount 99.3. Yeah, okay. And so this one here, this is your sample mean, okay? And this is your hypothesized mean, X bar. And so this one has to be the one that you think it's going to be, which is this one right here. And then this one right here is the actual observed mean, I think. All right, let's go check. It's been a while since I've done this one. All right, so but the problem is going to ask us, so find the probability of observing sampled needles of blah, 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 or less. And then so go back to here, and this here's probably less than and probability greater than. Okay, and so yeah, I can tell you right off the bat that these are backwards. So I'm sorry, I keep screwing this up. All right, so 0.993. Okay, so this is mu. All right, mu is going to be whatever the population mean is. All right, this one here is x bar. That's going to be your hypothesized mean or whatever your sample mean is. Okay, and so the probability of getting one that's actually less than this is actually going to be really small because we expect an average of 1.02. And so 0.06 is going to be our answer there. So 3 decimal places, 0.066. Check. Ta-da! All right, let me do another one and not screw it up for you. So, here we go. All right. Blah, 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 blah. It's a group of organs. Blah, 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 blah. So, in lubricants and electrical, disposable items containing less than 50 parts per million is generally not regulated. A certain kind of small capacitor contains PCB with a mean of 47.6 and standard deviation of 5. So, let's go over here. 47.6, standard deviation of 5. We're going to pull a sample of 38. So 38 in there, and then hypothesized mean. So my x bar, which is less than 49. So this one. So sample mean, that's your x bar. And so that's one goes in here. There we go. And then it was asking probability. Find the probability that the disposal of such capacitors will be regulated. And then so, disposal of items containing less than 50 parts per million. So this is a sneaky problem here. Will be regulated, so it would be greater than 50. And so we got to go back in here and do 50. Probability less than 50, greater than 50. 0.891. Certain kind of contains PCB. Oh, okay, never mind. I don't know why it has this extra information in here. Planning to regulate the disposal of 49 ppm or less. And so, yeah, we were actually okay on that one. And so this one is 47.6. My bad. God dang, man, I was just getting screwed up in the reading right there. All right, so the probability that it'd be regulated, which would be greater than 49, would be this one right here, 0.042. Done. Check. Yeah, see, they put this extra piece of extraneous information in here. Stupid Alex. So don't be messing with me like that. All right, one more. And this will kill off our purples. All right, so mean salary offered, blah, 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 24,260 with standard deviation of 3712. 24260. 24260. Standard deviation 3712. 3712. Sample size in this one, 80 students, and their mean is 24,500. 24,500. So probability is more than that. So they're looking for is greater than that. And so there you go, 0.282. 0.282. All right, so bam. Done. All right, cool. So with central limit theorem in particular, just make sure, I mean, you can go through and you can do it in the Alex calculator. It's not hard. All right, so just make sure that you're using the formula. And remember, that's mu minus x bar, or I'm sorry, x bar minus mu all over the standard deviation over the square root of your sample size. All right, it's not a difficult formula. It's pretty easy to enter in the calculator. But at the same point in time, if you don't feel comfortable doing that, just use my Excel spreadsheet right here. Fill in the yellow boxes. Make sure you look at the right ones, because sometimes they ask you for less than, sometimes they ask you for greater than. That's all that these two things are doing right here. Okay, it was using this P key right here. Exact same thing. All right, cool beans. Here we go. All right, more Sabrina the Teenage Witch. Here we go. There are so many questions on this, it's not even funny. So let me see. Here's a great one. What is Salem's mom allergic to? What is Salem's mom allergic to? There you go. Here we go. Hip hip hooray! Yay! Finish on that. Salem's mom is allergic to what? Nothing to show. All right, confidence intervals and hypothesis testing. Nothing? Nobody? Did we lose everybody? Ah, there you go. Yeah. Squidson, you already answered that one, though, so Guts gets this one. So, Squidson, you got pancakes right, and so I'm not going to give you two in one day. But Guts, you got it. Yes, and Harley, you are correct as well, but it is Guts beats you to it. It's cats making Salem's mom allergic to Salem. All right, so let's move on here real quick. So as soon as you start pushing into the dark blues, the first thing that you're going to run into is confidence intervals and hypothesis testing. So there are a couple in this one that are a little bit tricky to do up front, and so it's usually best to do those first. And so that's this one here, selecting a distribution for inferences on the population mean, determining the null and alternative hypothesis. This is going to open up hypothesis testing. So don't get jammed up on this one until you do everything out there that says confidence intervals on it first. Okay. Because this one here, I think this is the one that you should do. You can do this one right off the bat, but I would start with the confidence interval ones first, okay? Because these are related towards hypothesis testing, all right? I know I have videos up on them. So over here, let's go ahead and do this one, all right? Because I want to show you how to do confidence intervals really, really quickly. So what is a confidence interval on a standard normal distribution, whether it be the standard normal like Z or student's T, which is still normally distributed. A confidence interval, well, actually, it works on all distributions. We're just going to do it on Z and T first. So what a confidence interval is it's when we use a sample, all right, and we take a look at that sample, and we say, okay, it's, central limit theorem. We got enough people in here. And then we actually can use the sample mean to predict the population mean, or any statistic within the population, all right, typically mean. All right, and I think all the problems here are mean. But we can't do so with absolute certainty. We can't say that we're 100% sure that it's that way. That's not how central limit theorem works, okay? But we can do so with a certain given level of confidence. And so we could say, well, I'm 95. I can do so with a 95% level of confidence. All right, I got to get my terminology correct because math nerds or stats nerds, they get all upset about this stuff if you jack it up. All right. So, but I can say with a 95% level of confidence that, the mean falls between this and this. And that's what these two things are. And so you get an upper limit and a lower limit. And we're going to say, yeah, we're 95% sure that the mean falls somewhere between these two things. Okay. For the population, you're just using the sample. All right, so this is really easy to calculate. So don't be intimidated by these at all. In fact, you got the calculator right here. This is all you need, okay? Because all you really need in order to do these problems, and you look at this formula here and you're like, yeah, trust me, it's not as bad as it looks. All right, all you need to do either side of these, all right? So because this is the lower limit here, here's your mean right here, and here's your upper limit. All you need is the mean, all right, so in this case, the sample mean, x bar, added to this little formula right here, which is the confidence interval formula, all right, which is this guy, all right? X bar minus mu all over your standard deviation divided by the square root of your sample size. That's it, okay? All right? And so to figure this one out, let me just show you how to do this one in the calculator here real quick. So the first thing that you need to start with on this one is the confidence level. All right, so if we have, here we go. So based on the sample, find the 99% confidence interval for the true mean breaking strength of all cables, okay? And so to do that, we're going to use this guy right here, our Z box, to figure out, okay, what's our Z value, our cutoff value right there. And so this one's going to be 0.99, so 0.99, bam. Negative 2.32, that is not correct. Oh, I know why that is because we have to take 1 minus 0.99, okay, then chop that in half, and now punch that in here, and bam, there we go. So see how we got that? And the reason for that is because whenever we're doing confidence intervals, remember, we're looking at both sides of the equation, all right? And so you got to take, I want 99%, and so that's leaving me with just 1%, so it's 0.5% on either side. All right, and that gives me my value right here that I can use. All right, and then so to do the rest of this problem, it's pretty straightforward. You just take that, and then you multiply it by the standard deviation, 101, which is divided by the square root of your sample size, which is 60, like that. Oh, and then make sure you hit your arrow key twice to get out of there. Bam. Okay. Ta-da! And so 33. Now you're asking, what is 33? 33 doesn't mean anything. You're absolutely correct. All right, you have to take this 33 and you have to add and subtract it from your mean right here. So if you add and subtract that from the mean, you get, there you go. There's your two answers right there. Now that might be a little bit tricky, but I just wanted to show you the entire step process all the way through. Let me show you how to do these real fast here. Okay, I'm going to show you two different ways. All right, the first one is to take your mean like this and then hit this plus minus key right here, okay? And then do your Z table lookup like this, and it's going to be 0.99. But remember, it's going to be half of that. So it's 1 minus 0.99, okay, divided by 2, all right? So 1 minus 0.99 is 0.01, divided by 2 is 0.005, right like that. And then all you have to do at this point in time is take your standard deviation divided by the square root, like this, of your sample size, which is 60, arrow over twice, close parenthesis, and ta-da! There you go. You get your exact answer, exactly, both of them in the same entry right off the bat. So there you go. 1764, lower limit, 1783, upper limit, right there. All right? So that's one way to do it. Let's go ahead and practice a couple. All right, here we go. So real straightforward, blah, 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 stuff from the problem, don't care. All right, all I need is my mean. So these have a standard deviation. Where's my mean? Find the true mean of the lifetime of bulbs. So it has a mean lifetime of 482 hours. There we go, 482. Plus minus, and 90% confidence interval. So 1 minus 0.9 is 0.1, chopped in half is 0.05. So Z 0.05, open parenthesis, 55 hours is my standard deviation divided by the square root of my sample size, which is 50. Arrow over twice, close parenthesis, dunzo dunzo. 469.206, and this one is 494.794. Check. Ta-da! Let's do another one. Real easy. Not even going to read the problem. Don't care. I got to pick out my mean. Here's my mean. Chloride level 103. Whatever's. 103 plus minus Z. All right. My confidence level in here is 99. So 1 minus 99. 0.01 chopped in half. 0.005. 0.005. Open parentheses. Where's my standard deviation? Right here. Standard deviation 36 divided by the square root of my sample size, which is the 70 right there. 70. Arrow over twice, close parenthesis, oops. 70, arrow over twice, close parenthesis, bam, dunzo dunzo. There we go. Lower limit 91.916, 917, whatever. And 114.083. Check. Ta-da! All right, so you can do them that way using the Alex calculator. The other way that you can do this is go on over here to Module 4. hypothesis testing, and ta-da, you can use my confidence interval spreadsheet. So download this guy. This guy is going to make your life so much easier. So you can do them with the calculator, or you can do them using this. All right. So the only thing you have to be careful on this one. All right. And you guys might have a little trouble seeing this, depending on whether or not it's actually showing. I'm going to have to check the feedback on the stream here real quick. Is there are many tabs on this this spreadsheet here. Okay. Yeah, you guys can see them. So, all right, so there's multiple tabs on this spreadsheet here, and you're going to use a different tab depending on which problems you're actually getting. So this problem that we have right here, get out of that, in Alex, this one here, confidence intervals for population mean, use of the standard normal. This is Z distribution, so in Z distribution, we know what the population standard deviation is. And so you're going to use this one here that says population standard deviation. Down the road, there's going to be another one where you're going to be using the T distribution. Okay, that's where sample standard deviation is all what you know. You only know that. You don't know population standard deviation. In that case, you're going to use this tab here. There are other ones down the road that are on proportions. Proportions use the Z formula, okay, but there's slightly a little different change to it. For those on that, the confidence intervals on those, you're going to use this tab here, which is proportions, okay? There's also one on variance in there somewhere. We'll be using this one on that one. There's also one where it wants you to calculate sample size. You use this one here. They're all the same formula, okay? And so I put them all on a spreadsheet here just to make life a little easier for you. And so feel free to use this. And it'll put rocket skates on those confidence intervals for you in the beginning of the class. So let me show you how it works. All right. So here we go. We got another one here. This is use of the standard normal. So we know what our population standard deviation is. And so in this one, the only thing that I need to know on this one is my alpha, my population standard deviation, my sample size, and my mean. Okay. Alpha is just the complement of your confidence level. Okay. So my confidence level here is 99%. My alpha for this one is going to be 0.01. Okay. That they're interchangeable terms, okay? It's just sometimes we use alpha, sometimes people say confidence level. Alex is going to flip it around on you too, so it's the exact same thing, just complements of each other, okay? Population standard deviation, so that's where I'm going to look at for this. Standard deviation, 10.8, so 10.8. Sample size is 90, and my mean has 73.1. 73.1, bam, there we go. So here's my upper and my lower right there. And so actually those are backwards, so that's okay. 70.16 is my lower. 70.17 is my lower. Oh, it just wants one decimal place. Got it. Can do. Oh, if you want to get fancy, you can just go up here and actually reduce these down. Bam, there you go. 76.0 is my upper. Check. Bump, bump, bump. Oh, look at that. I fat fingered that one. Boo. Bad Alex. Bad, well, bad Pat. All right, here we go. Let's do another one. Determines $17. So standard deviation is $17. Okay. Random sample 150. Mean daily wages are 119. So it's not giving me my other mean in here. Oh no, I only need my alpha. That's right. So my confidence interval 95. So my alpha is 0.05. 17. Sample size was 150, and my mean is 119. So my my mean for the population can be somewhere between 116 and 121. 106.3 and 121.7. Check. Done. Double credit. Yay. So you can do these either way. You can do them using the spreadsheet in the module 4 folder there, or you can do them using the calculator. I honestly, if you get used to using the calculator, it's almost as fast as doing this in the spreadsheet. So whatever works for you. The spreadsheet probably make you might not fat finger something quite as easily, but just make sure that you're actually putting the right information into each one of those boxes. You need the alpha, which of course is just the complement of your standard deviation or of your confidence interval. You need the standard deviation, you need the mean, and then you need the sample size. Those are the only four components of that entire formula, and it'll solve so many problems for you over the next few days that you should be able to rock out most of the blues, or at least the light blues until you get to hypothesis testing. And so let's see if we got another one in here real quick. So here's one for population proportion. I would do that one next. And then, yeah, then these are related to hypothesis testing. And so that's probably a little bit beyond the purveyance of what we're going to do today. But this one right here, just do it. So just go in here. Instead of using this tab right here, you're going to use proportions right here. That'll unlock this one, which is where you know sample standard deviation, use of the normal t, or the t distribution. And you're going to use this tab for that one. Just make sure, do I know the population standard deviation or not? If the answer is yes, then it's Z. So you're going to use this one. If it's no, then it's T. You're going to use this one. If it's a proportion, meaning it's a percent of a whole, then it's a proportion. You're going to use this one. All right, so that's it. They're that easy. Make sure that you're using this guy if you're jammed up on anything. Otherwise, feel free to do the formulas. So either way works for me. All right. Cool. All right. So, man, we did a lot of topics today, and we're dipping into the blues here, but we'll crush out a bunch of these next week, and then of course, unfortunately, the following week after that, we do have spring break, which I'm sure a lot of you are looking forward to. But I do have videos up on everything, so feel free to work ahead. And at that point in time, if you do have any questions, we'll do lab time again this Wednesday. So if you're jammed up on anything, please phone in. Okay, I will be there. All right, there to help you. All right, but in the meantime, I do have one more Sabrina question for you. Here we go for a free quiz or homework. Let's see. Oh my gosh. Oh, I remember this. Oh my God, what happened to Harvey when he first kissed Sabrina? Yeah, I remember this. What happened to Harvey when he first kissed Sabrina? What season was that? Oh, I can't even remember. That was early in the series. So, what happened to poor Harvey? We do have a little bit of lag here today. Yes, you got it, Harley. He did. He absolutely turned into a frog. All right, good for you. We got you another one today. So, well, no, yeah, that's right. You did the Stranger Things one in the previous one. So look at that. You got paid for being here today. So that's awesome. All right, guys, that's all I got for you here today on stats. Ping me in the next couple days if you get into trouble on anything. Otherwise, I'll definitely be there on Wednesday afternoon. Come on by or stop in on the Zoom, and I'll be more than happy to help you with anything you're jammed up on. But that's all I got for you today. Feel free to jump off here. I'll hang around for about another 30 seconds or a minute, just in case you have any questions. Take care now. Bye. Oh, yeah, that's enough, Alex. You bet, Morgan. Take care. Bye, Harley. Have fun. We'll see you. All right, about 5 seconds. 3, 2, 1. See ya.